Now we will start a new chapter, and in this chapter we will investigate the dynamics of the relativistic charge particles under the electric field and the magnetic field, and we will investigate the motion of the field itself, that is the electromagnetic fields. So far what we know that the four-dimensional Lorentz force, so let's say free index mu E over mc f mu nu. So if we contract through the nu, the free index will be the mu, and we have seen that the Maxwell's equations in covariant forms, so this is the four-dimensional Lorentz force in covariant form. So Maxwell's equations with the sources f mu nu, derivative of the f mu nu, del mu f mu nu is equal to 4 pi over c j nu. So if you contract the mu, nu will be the free, and using the dual field strength tensor, we derived at the homogeneous Maxwell's equations. So basically for all sets we will try to find that what is the Lagrangian, or what is the Lagrangian density for the fields. So from the classical mechanical point of view, we are studied at the least action principle. So if you have a Lagrangian depending on qi dot coordinate derivatives and time, the Lagrangian integrated a time interval is called the action. So if you have one point, if you want to go to the other point under any Lagrangian, so you have several options. You can fix the points, endpoints, and you have still several paths. So least action using the variation principle finds the extremum conditions such that one point to other point you could go. So you can divide this small time sticks, and you can look at this integral, and you can try to find that the extremum value of that integral. In particularly, minimum is important, but the least action can see that only the extremum conditions. So we need a Lagrangian in order to find that the covariant form of the four-dimensional Lorentz force, and we will see next time, maybe next week, we will need a Lagrangian density to describe that the equation of motions of the electromagnetic fields. So let us now start just try to find the Lagrangian for just a relativistic particle without interacting with the electric and magnetic fields. Suppose there is a charge moving relativistically. What is the Lagrangian for that? If it is moving non-relativistically, you know that the 1 over mv square Lagrangian is t minus v. No potential v is no v, only 1 over mv square. But we have problems with that kind of definitions, because we can talk about that in inertial frames we are saying that we need a covariant equation of motion. So 1 over mv square is non-relativistic but depends on the coordinates. In different coordinates v is changing. So if you look at the definition of the action, and let us try to estimate what kind of Lagrangian we can propose such that the action is the same everywhere and we can write the correct equation of motion using the Lagrangian. What is the equation of motion for the Lagrangian? If you take the variation, you will find d over dt del over del qi dot derivative of the Lagrangian with respect to the derivative of the coordinate minus del L over del qi. This is the coordinate dependent, this is the velocity dependent. So, you know one thing, time is not unique, but you know that the proper time is unique. It's the same in every observer with respect to the observer. So, the relation between the dt and d tau is simple. It's a gamma factor. So this is the proper time is the same everywhere. Everybody agrees that the proper time is the same everywhere, every observer. So instead of dt, you can write gamma d tau times Lagrangian. And now d tau is invariant, gamma is variant. So different observers have different gammas. Gamma is related with the velocity. So you can automatically see that your Lagrangian have to be in the form of what? So if you want to make this hold, d tau is invariant. That is the same everywhere. So proper time. But gamma is different, and we want the action is invariant. Therefore, this stuff here, L gamma, should be invariant. This should be some Lorentz invariant, or we will call later Lorentz scalar. So you can see that for free Lagrangian, no electric field and the magnetic field interaction, you can guess that your Lagrangian should go some 1 over gamma, because we can cancel this. One of the thing. The other thing, what tools we have as a Lorentz invariant? Charge, we don't, charge is the charge, so it's a observational thing. So the best thing is to think about that the 4 vectors, scalar product of the 4 vectors and so on. One tool, you know that speed of light. Okay, so speed of light is invariant, and you know that as a, if you write that the proper time, for velocity, I am sorry, with respect to the proper time, for velocity with respect to the proper time, that is gamma c, gamma v, and gamma u. So if you take the scalar product by itself, you will get c square. So you can introduce that your Lagrangian should be containing some c square. So c square is the scalar product of the 4 velocity by itself. You can introduce, in order to give the dimension, you can put m or alpha, then you can put the dimension later. So let us put the m or alpha. The sign could be negative or positive. So if we choose such a Lagrangian, first can we find that the equation of motion correctly? Or second, what is this in non-relativistic limits? So the non-relativistic limit could be seen very easily. So the free Lagrangian plus or minus mc square over gamma is 1 minus u square over c square. This is 1 over gamma. So in non-relativistic limit, this is small, you can make a binomial expansion. 1 minus 1 over 2 u square over c square. There are other terms, but ignore those things. You will obtain what? Plus or minus mc square minus 1 over 2 m u square or v square. So if you want to go to the non-relativistic limit, if you say this is alpha, alpha should be m. If you put plus, this will be minus. If you put minus, that should be positive. So the conventional choice is to choose the Lagrangian with the negative value. That will be the same for the Lagrangian density for the electromagnetic field. So this is the Lagrangian for a free charge particle, no interaction with the electric and magnetic field. So if you plug this here, this action will be invariant. So then you can look at whether this Lagrangian is working well or not. You can look at the equation of motion. So we don't have 1 over mv squared. And another thing, so if you put minus, that should be plus. Mc squared is constant. In the equation of motion, putting, adding, subtracting to the constant doesn't affect, okay, because you will take the derivative. So the other thing you can think about this, if you put the minus sign and the plus sign, there's another little difference also. If you say that no motion, gamma is 1, if you put minus, the action will be the minimum. If you put plus of this value, the action will be the maximum. So actually, Euler Lagrange sees only the extreme conditions, but this minus sign is detected the minimum of the action also. So if you calculate that the equation of motion and the free Lagrangian is here, so L free is minus mc square 1 minus u square over c square. So if you take the derivative of the Lagrangian with respect to the u, equate to 0 because there is no coordinate dependence, free charge particle. So if you take the derivative, you will obtain d over dt of what? If you take the derivative with respect to the u, you will obtain what? Minus 1 over minus 2 minus plus, and you will obtain mu over 1 minus u square over c square is equal to 0. So if you take the derivative of this free Lagrangian with respect to the u, you will obtain 2 times 1 over 2, and this goes to the down as a minus 1 over 2, and you will obtain that. And what is this? What is this? This is nothing but gamma. d over dt gamma mu is equal to 0. And what is the gamma mu? What is the gamma mu? That is the momentum of the relativistic charge particle. So I write the momentum of the energy of the relativistic charge particle multiplying the 4 vector by m, and I give you that as a homework. You can find the same relativistic energy and momentum using the collision. Now we define that the Lagrangian of the free charge particle, and we find that the equation of motion. So this term in the d over dt have to be momentum. So therefore, momentum is gamma mu. So far the Lagrangian for the free charge particle is working well. If you know that Lagrangian, you can calculate the Hamiltonian and the energy. So let us look at that, the energy and the Hamiltonian of the free charge particle. So as I said, there is no any interaction with the electric and magnetic field. So H is P dot U minus L. P is gamma mu dot U, and minus the Lagrangian of the free charge particle minus mc square over gamma. So you will see that gamma mc square automatically. So that is equal to what? Gamma mu square, gamma mu square plus mc square over gamma. So if you take the parentheses of gamma mc square, you will find u square over c square plus 1 over gamma square. Is this right? Gamma mc square makes, multiply this, that will be mc square over gamma, and multiply this, what will be gamma mu square. Okay, and go one more step, gamma mc square u square over c square, 1 over gamma square is equal to 1 minus u square over c square, and this will be cancelled. So the energy will be what? Energy will be gamma mc square, relativistic energy. Okay, so we define this, but using the Lagrangian we find this. So this Lagrangian working well. And if you go to the low speeds, you can again use that the limits. So what is this? The energy, relativistic energy, is gamma mc square, and that is equal to mc square over 1 minus u square over c square. And if you are working at low speeds, this energy is equal to what? mc square 1 minus this goes as a up as a minus 1 over 2. So in the low speeds, the surviving term will be the u square over c square. Ignore the higher orders, so do a binomial expansion. So I think this is plus, and that is c squares will be cancelled, and you will obtain that the energy is equal to mc square plus 1 over 2 mu square and the other terms. So again, at low speeds, you have the 1 over mu square plus mc square is constant. So if you calculate the Hamiltonian equations of motions, constant doesn't affect it, and you will find that the equation of motions easily. So far for the Lagrangian for the free charge particle, and how we can include this Lagrangian to the interaction with the electric and magnetic field. So let us define that, then we can stop and study next time. So in this business, let's look at what we have in the non-relativistic case. So in the non-relativistic case, T minus V, how we define that the interaction of the electric charge with the potential. What tool do you have? for the V. Only tool you have scalar potential. Okay, so electrostatic scalar potential phi. If you multiply with the charge, you can define that the interaction of the charge with the potential in non-relativistic case as in that form. Minus, because of V is minus. But this is not enough if the charged particle is relativistic. So what tools you have in order to make the action is invariant? In order to work with the action as invariant, you need some Lorentz scalars. So what we have as a 4 vector, u and u is c square. Another thing, another piece, we have 4 potential. And the 4 potential is this. And if you look at in the non-relativistic piece, you are seeing that this piece, you don't see the vector potential part. And you need a scalar such that action doesn't change as a Lorentz. If you find a Lorentz scalar such that the action doesn't change, you can write that the equation of motion, and you are feel that show that that equation of motions are covariant in all inertial frames. So basically, so far the tools are the 4 velocity and 4 potential. So if you multiply this, if you take the scalar product of u alpha and a alpha, what you are going to obtain? Gamma c phi, and what is the other term? Gamma c v minus gamma v dot a. Is it a scalar product? Yes. Is it the same all frames? Yes. So is it related to this one? Not yet, because this is E phi and here you gamma c. But if you divide the things minus E over gamma c with the side by side, gamma c's will be cancelled. You will pick up the non-relativistic part as a minus E phi, and you have the additional term there. So that whole piece is the interaction part of the relativistic Lagrangian. So let's say relativistic. But are we satisfied? No. We try to find that there's some scalar which is Lorentz invariant such that the action and the equation of motion will not be changed in different frames. We find something. We have to show what is this Lorentz force. Is this Lagrangian interaction plus the free Lagrangian is giving the correct equation of motion. So next thing we have to work on this. But let me write at that point, let me write the whole Lagrangian. The Lagrangian is L free plus L interaction with the electric and magnetic field, which is relativistic. And that is equal to minus mc square times gamma, 1 over gamma, 1 minus u square over c square, and plus the interaction term. So interaction term should be what? Gamma c will be cancelled, 1 of the gamma will be cancelled, and this should be what? Plus E over C plus E over C U dot A minus E phi. So did I write correctly? Gamma C will be cancelled. Minus E phi is the non-relativistic part, and minus plus gamma is cancelled, and E over C V dot A or U dot A. So this is a Lagrangian for the charged particle moving in the electric and magnetic field. If you calculate that the earlier Lagrange equations, you have to find what? Lorentz force. And then as an exercise, do this to the next time, and I will calculate the Hamiltonian, and I will see that how the energy and momentum will be modified. We will define that for momentum, and the momentum will be, so energy part will be modified by scalar potential, and the momentum will be modified by the vector potential as a canonical momentum. So far, take this piece and try to calculate that the earlier Lagrange equation and see that find that the Lorentz force. So basically, we are looking at Lorentz scalars such that the action will be invariant. Then variation of the action give you the equation of motion. Then those equation of motions will be what? Covariant in different Lorentz frames.